In this lecture, we're going to continue our study of confidence intervals. So far, we've learned about confidence intervals for a proportion, when we're trying to estimate the probability of something occurring, whether it's flipping a bottle cap and it coming up red, or whether it's surveying a voter and seeing if they're going to vote for the candidate. Now we'd like to extend that to other kinds of data where we're trying to estimate the true mean of the data in terms of a sample. So to start off, let's remember what we did for proportions. Let's go back to the bottle cap experiment. And in that case, we estimated the probability of getting red just by what we called p hat, the fraction of times that we got red from the data. And then we said, well, this p hat, we know that its mean is the true p, so that's good, and its variance satisfies a certain formula. But also, this proportion is made up of sort of a sum or an average of a bunch of different influences, so the central limit theorem says that it's approximately got a normal distribution with that mean and variance. Once we know that, then we can rejig it to get something that has a standard normal distribution, and then we can get a range that 95% of the time it will be within, and then we can do a little more manipulating and end up with a 95% confidence interval. We also had the problem that this confidence interval was in terms of p, and p was unknown. Well, but we can substitute p hat for p, or we can substitute a half for p to be more conservative, and either way, we get a confidence interval. Now, let's consider the data that Allison presented last time about the number of years younger that 60 different patients were perceived after undergoing plastic surgery. Now, the data in this case consists of the number of years younger that each of the 60 people is perceived. So the first one was 2.8 years younger, the second one was 9.1 years younger, and so on, up to the 60th one, who was 5.7 years younger. So what we'd like to know is the true mean value for the general population of people who undergo this plastic surgery. That's the theoretical world, and we'd like to know the theoretical or true mean value, which we'll call mu. But all we have are the data. Now, we already know that we could try to estimate mu by x bar, the sample mean, the mean of those 60 numbers that we got, the average. But does that mean we're sure that on average exactly 7.177 years is the perceived amount younger when anyone undergoes this plastic surgery? No, there's some uncertainty in the value of mu, and we would like to get a confidence interval for mu again. Well, just like last time, we know some things about the sampling distribution of this x bar. We know that on average, it equals mu, the true mean, so that's good. But we also know it has some variance. In this case, the variance is equal to sigma squared over n, where sigma squared is the true variance of the number of years younger perceived of all the people who get this plastic surgery. Now, again, this x bar is made up by averaging a bunch of different values, in this case 60 values. So again, the central limit theorem says that approximately this x bar has a normal distribution with that mean and that variance. Well, from there we can proceed exactly as we did before. We can say, okay, we'll subtract off the mean and divide by the square root of the variance to get something that's a standard normal, and then we'll use this figure of 1.96 as the possible plus or minus range for the standard normal to happen 95% of the time, or 19 times out of 20, and then we'll rearrange that a little bit just like before and end up with a 95% confidence interval for the true mean mu in terms of x bar minus 1.96 times the square root of sigma squared over n, and x bar plus 1.96 times the same square root. So now we have a confidence interval just like before. The problem is, just like before, it's in terms of an unknown value. The last time the confidence interval was in terms of p, which was unknown, but we had some tricks for how to make a substitution. This confidence interval is in terms of sigma squared, which is the true variance of the different number of years when different people get plastic surgery. And of course, we don't know that either. So what are we going to do? Well, let's start by remembering that formula that we had a while back for the sample variance and the sample standard deviation, which allowed us to try to estimate the variance and the standard deviation S from a sample. Maybe that will help us here. So here we have a confidence interval but in terms of this unknown sigma squared. So maybe we can just substitute in s squared instead of sigma squared. Well, we almost can. There's some good properties there. For example, the expected value of s squared turns out to be exactly the true unknown variance sigma squared. So that's good. And in fact, that tells us why we divided by n minus 1 instead of n when we had that formula for the sample variance. It turns out, though, that when we try to now use our usual trick of subtracting off the mean and dividing by the square root of the variance, well, now it's sort of a sample variance, and it's not quite the same, and it turns out we get a slightly different distribution. It's not actually the standard normal distribution, but it's pretty close. It's something called the t-distribution, with n minus 1 of what are called degrees of freedom. It's just a parameter for us. But we have this new distribution, which is almost like a normal distribution, but it's not quite. To illustrate that, we can look at a couple of graphs. Here's the standard normal distribution in blue compared to a t-distribution with only 3 degrees of freedom in red. And we can see they're pretty similar, but the t-distribution is a little bit wider, corresponding to having more uncertainty because we didn't know the true variance. We had to estimate that too, so it made things more uncertain. But as we go up to higher degrees of freedom, it gets closer and closer to a normal. Here it is comparing a standard normal to a t-distribution with 10 degrees of freedom, and we can see already they're quite close. So the t-distribution is pretty similar to the normal distribution, especially when the degrees of freedom are large or when you have lots of samples, but it's a little bit different. So how does that help us? Well, if we go back to that case of the number of years that we perceive people to look younger, well, we had a 95% confidence interval in terms of the true variance sigma squared, but if that's unknown, well, we could replace it by s squared, but then we would also have to use the t-distribution. The t-distribution in this case has 59 degrees of freedom because it's n minus 1, and n was 60 was the sample size. So you might think that's going to change this number 1.96. How is it going to change it? Well, here's a table which gives some of the values, which you can look up in a book or you can get the computer to tell you. And they say if you're making that 95% confidence interval, well, for the normal, you use that number 1.96. For a t-distribution, you have to use slightly larger numbers because we have slightly more uncertainty, so we need a larger interval before we're just as confident. But the amount you need, which is larger, isn't that much larger. Even with only 3 degrees of freedom, okay, well, it's from 1.96, instead you need 3.18. But as you go up to 6 or 10 or 15 or 20 degrees of freedom, it's getting pretty close to that 1.96. By the time you're up to 59 degrees of freedom, which is what we have here, it turns out to be exactly 2.00 as the number you need instead of 1.96, just a little bit larger. And as the number of degrees of freedom get larger and larger, it gets closer and closer to that same 1.96 as for the normal. So returning to our calculation, we can say we've still got that same confidence interval, except we need to replace that 1.96 by a 2.00. And then we can compute the confidence interval the same as before using our value x bar and also using this s squared value. And when we plug in the numbers for that data, here's what we get. And it works out to an interval between 6.42 and 7.94. So this tells us that the true mean of the number of years was somewhere between these two numbers. And that's how we get a 95% confidence interval for this mean, this unknown mean in terms of number of years. Or for another example, let's consider again our old friends, the skeletons. In that case, we had 400 observations, so n was 400. For each one, we had the difference between the estimated age and the actual age at time of death, and the mean of those 400 different age differences turned out to be about minus 14.15. And the sample variance of those 400 observations turned out to be about 199.5. So what if we wanted a confidence interval for the true mean of the age differences? Well, it turns out that if n is 400, so there's 399 degrees of freedom, then the value we want to use for a 95% confidence interval, instead of 1.96, well, is about 1.966, so just a tiny bit larger. And we can plug that in and we see we get a 95% confidence interval for those age differences, for the true mean of them. Or maybe we only wanted a 90% confidence interval. We didn't need to be quite so confident. Well, in that case, instead of the value 1.645 for the normal, turns out we use a value about 1.649, just a tiny bit higher again. And we can plug that in, and sure enough, we get a 90% confidence interval for the true mean of those age differences. So whether we're studying skeletons or whether we're studying anything else, if we have some data and we want to know the true mean, and all we have is a sample mean, then we can use these simple properties of the normal distribution and the t-distribution, which is almost the same, in order to get approximate confidence intervals. And that gives us a range of values that we're pretty sure include the true values.